Okay, well that was weird. My IP got leaked. Not leaked, but it just showed up on screen. So I had to restart. How does this website not come out with the abbreviation? Come on, Paul. Fix the site, man. See, I did like most of the graphing examples off stream. Well, on stream, but it's gone now. Unfortunately. Stream for about an hour. Just wanted to make sure my coast graph was normal scale. Pi over 2, pi, 3 pi over 2, 2 pi. Okay, I got that right. So this is the same thing, I think, if the sine, yeah. So for 13 we got one, two, three, 4. Pi over 2, pi, 3 pi over 2, 2 pi, negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi, 1, and negative 1. Okay, so the sine starts at 0. It goes like this, 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 and that. And then it goes the opposite way. So it's like this. Wait, no. Or wait. No, it goes like this, actually. Never mind. You know, I think I got cos wrong, maybe. Or no, cos is right. Okay, it was a sine. This graph, you can see that sine is the same range. Sine itself will never be larger than 1 and never smaller than negative 1. Then we got tan. Okay, so for this one I don't remember it because there's asymptotes in it. So calculator. Um, 1.5574 negative 1.557. Wait, I should be plugging in. How do you graph tan? How do you graph tan? Here, tan of pi. Okay. 0. I should probably do pi over 2 first. Okay, undefined. There we go. Undefined. Because that would be like this point in the unit circle. Since sine or tan is sine over cosine. It's 0, 1. So it'd be 1 over 0, which is undefined. Okay. And then 3 pi over 2. Would that be 1? Or wait. Negative 1? Wait, it's also undefined. Oh wait, yeah, I forgot 3 pi over 2 is it's this point at the bottom. I was thinking of pi. Never mind. Undefined. And then 2 pi. This should be 0. Pi over 2, pi, 3 pi over 2, 2 pi. I think it goes like this. Or something. And then the opposite, I'm not even gonna write out the points here. It looks something like this. Sure, let's see. In the case of tangent, we have to be careful when plugging x's in, since tangent doesn't exist wherever cosine is 0. Remember that tan of x equals sine x for cos x. Tangent will not exist at these. Yeah, so. Oh wait, the end shouldn't be like that. They should all be going the same way. I was right on the left, but not on the right. Should be like that. Alright. 15. Y equals secant x. So wouldn't just be sine, a sine graph? Or wait, okay, if you think about it. Let me draw this out, if it'll let me. What is going on? Layer 1 copy, what? What is this? Dude, just let me draw, man. Oh, it's because of that, okay. So we got triangle, theta, x, y, r. Or wait, 1. Secant would be if cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. So it's 1 over x. So when you're plugging something in, 1 over pi. Alright, let's see the example, honestly. So, as with tangent, we have to avoid x's, for which cosine is 0. Secant x equals 1 over cos x. Okay. So, which one's the cos? This is the cos one. So where does cos equal 0? Pi over 2. Pi over 2 is one of the asymptotes. And so is 3 pi over 2. So we got pi over 2. I'm not going to work these out. And then for the others, 1 over 1 So y equals 1 for this. At 2 pi, it's the same thing. I think it's the same for all of them. Wait, this is negative 1. Wait. So I think this would be negative 1. This would be 1. Then negative 1, 1. Yeah, okay. I think it goes like this. Then at 0, there's also... Oh yeah, because the peak. There, okay. And that's all of them. Notice that the graph is always greater than 1 or less than 1, negative 1. This should not be terribly surprising. Yeah, okay. Note that we did not graph cotangent or cosecant here. However, they are similar graphs of tangent and secant. You should be able to do quick sketches of them, given the work above if needed. Finally, note that we did not cover any of the basic transformations that are often used in graphing functions here. The practice problems for this section have quite a few problems designed to help you remember them. If you know the basic transformations, it often makes graphing a much simpler process. So if you're not comfortable with them, you should work through the practice problems for this section. That's alright. We're good. Alright, it's time for limits. Actual calculus, no shot. What is this, the 11th video? Time for real calculus. Let's get my man Professor Leonard in here.
So let's get started with our actual calculus stuff. Oh, this is gonna be awesome. So with our calculus, we're gonna talk about...
Alright, just in case I want to take notes, I'll write this down. Professor Leonard. 1.1 limits.
Limits first. Now, our limits is really the basis to our calculus. It's how we do calculus. We're going to find out some kind of tricks to calculus later, but for right now, if you know how to do limits, you're going to be able to do calculus. So it's probably a pretty important idea, yeah? Yeah. So we're going to find that out towards the last part of this class. For right now, I want to lead you through an introduction to calculus and what it's all about. Are you ready to learn that? So review is over with. Thankfully. Now we're going to slow down just a little bit. We're going to talk about actual calculus stuff. So no more really hair-raising, kind of, oh my gosh, so much stuff. We're going to go a little bit slower, but it's going to be more in-depth. You ready for it?
Yes. I think yes. Slower may sound good.
Slightly slower, not much slower. In calculus, we have two basic goals in Calculus 1, this introductory course of calculus. So here are our two goals. Goal number one. The first goal, and the one that we're going to spend most of our class on, at least the first half of our class on, is this goal. Given any curve, not straight lines are easy, but given a curve, I want to be able to find the slope of a curve at a point. Isn't that an interesting idea? If I say to you, I want you to go ahead and find me the slope at that point. Right now, we really have no idea how to do it.
That's
I mean,
crazy.
You can approximate it. You can go, oh, okay, I'll find the slope. Let's see, slope is 1/2. Is that accurate? No idea. Right? Well, we can't really just kind of approximate slope. What we're going to do is find out a really good way using calculus on how to find the slope of a curve at a point. In fact, when I ask you a certain thing in this class, you're going to say, oh, it's the slope of a curve at a point. We're going to talk about that for a long time. That's goal number one. Goal number one is to find the slope of a or to find the tangent to a curve at a point. The tangent is the line that intersects a curve at one and only one spot in an area. So goal number one, find the tangent which involves the slope of the curve at a point. That's goal one. If we can do that, we're on calculus fast pace. That's good. So we want to take a curve, be able to find the slope of that curve at a point. That's going to lead to the tangent and vice versa. Tangent and slope go hand in hand for us. Goal number two, which is the last half of our class, maybe a little less than that. Goal number two is also a really interesting question. So cool. By the way, this stuff is stuff you can't answer in any other class, right? You can't do that with algebra. There's no way you can do that with algebra. You can't find the slope of a curve. Are you kidding me? Slope of a straight line? Easy. Slope of a curve? Wow, it's weird. Is that not an intriguing idea to you? It should be. If you're in this class, you'd be like, oh, that's kind of cool. How are we going to find the slope of a curve? I don't know. Calculus. The next question is probably even a little bit more interesting. Next question is, let's suppose I have some funky, any curve that you can think of as long as it's defined by a function. Can you, between 2 points, find the area under that curve?
No, what?
Can you do it?
What did he just say then?
The answer is right now, with what you know, can you do that with geometry? Because I could say, okay, great, find the area of something that's curving. Can you do that? No.
That's crazy.
No, you can't use the area for a rectangle, that's not a rectangle. You can't use the area for a triangle, that's not a triangle. You can't break this up in any way that you have geometric figures, can you? Not even circles, not even with radiuses, because the radius is changing. So the next question is, can you find the area under a curve? Those are the two goals of calculus. Find the slope or the tangent of a curve at a point, and secondly, can you find the area under a curve between 2 points?
No, I don't believe him. Not possible.
Interesting stuff, weird stuff, right? It's crazy questions going on here.
Absolutely impossible, dude.
And amazingly, it's actually not that hard. I think it's easier than pre-calculus. It's easier than that. You don't have to do, maybe not easier, but if you know pre-calculus, this is not such a reach. What we're going to talk about first, we're going to talk about the tangent problem. I'll give you a very intro to this, but I'll talk about it later on. We're going to talk about this for most of our day-to-day. So let's talk about the tangent problem. Are you ready? Do you have any questions on the ideas of the goals of calculus? Do you understand what the goals are? The goals are A, find the tangent or the slope of a curve at a point. That's what we want to do. Goal number 2, after we finish this, we're going to move on to find the area under a curve between 2 points. Very cool ideas. So let's work on the tangent problem right after that. You're lucky you're here today. Okay, this is it. This is like the fundamental idea of calculus. This is so cool. We're going to figure out what a limit is from doing this idea right here too. Here's the tangent problem. The tangent problem says if you give me any arbitrary curve, so I'm just making up, I don't even know what that is. It's just an arbitrary curve, and you give me a point. Let's call that P.
It's good stuff. Gotta write it down, man. So we got our curve, and then P.
Give me a point, call it P. I want to be able to find the slope of that curve at point P. Do you get the idea? Talk about the tangent problem right now, right? Slope of that curve at that point. Because if we have the slope and we have the point, we can make the equation of a tangent. Do you get me? That's pretty easy. That's just y minus y1 equals mx minus x1. So right now we have the point. What we're worried about is the slope of the curve at the equation of a tangent. Do you get me? If we have the slope and we have the point.
What are all these sections here? Intro, goal, slope. Jeez.
We can make the equation of a tangent. Do you get me? Do you get the idea? Talk about the tangent problem right now, right? Slope of that curve at that point. Because if we have the slope and we have the point, we can make the equation of a tangent. Do you get me? That's pretty easy. That's just y minus y1 equals mx minus x1.
Because point slope. Yeah.
So right now we have the point. What we're worried about is the slope of the curve at that point. Do you follow? Now the problem is this. If we're going to make a tangent line, how many points do you need to make up a line? How many points do we have? That's the problem, right? How are you supposed to make the equation of a line? What is this? If we're going to make a tangent line, how many points do you need to make up a line? How many points do we have? That's the problem, right? How are you supposed to make the equation of a line when you only have 1 point and you don't know the slope yet? Do you see the issue? That's
a big problem.
So here's what we're going to do. We're going to say, okay, well, let's put some points somewhere else on this thing. How about Q? Up there.
Okay.
If I connect these two things,
Connect them. Oh, I really want to know where he's going with this. It's a little crazy, dude.
if I connect those two things, do you remember what it's called when you connect 2 points together? It's not a tangent, it's a, do you know?
What?
It's a secant line. If you've had some geometry, a secant connects 2 parts of well, usually a circle, but of any function. So we would say that PQ is a secant line. It touches 2 points of this curve.
I don't get that. What? Secant line. Secant line versus tangent line. Tangent line, line that intersects the circle, but only at one spot. Secant line, line that intersects the circle, but in 2 spots, continues through. Oh, okay. So this intersects 2 points. The tangent line would be like this or something. Intersects 1 point. Why is it called that? Why is a tangent line called a tangent line? A line or plane that touches a curve or a surface at a point. Dude, okay, that was so confusing. I was like, why is he talking about tangent like trig? The origin of the word tangent in this context is not trigonometry, although it has been adopted for use in trigonometry. So it just means to touch. Okay, dude. Jeez, man. So this has nothing to do with like the tangent of like trig. It's just, that's what it's called. And then a secant line is when it touches 2 points. Secant, literal meaning. To cut. Okay. Cuts the circle in half. Okay. I'm back in. Locked in. Absolutely. Q. Secant line.
Now here's the question, all right? You agree that we need 2 points for a line, yes? But we also agree that we want the tangent of point P. That's the ultimate goal here. So my
Yeah, and that's a secant.
question to you is,
So we don't want
is PQ a good approximation for the tangent?
No.
Is this a good approximation for this? Okay, it's an approximation, right? They're both positive, okay, sure. What I'm asking you is there a way, think about this for a second, is there a way that I can make this secant approximation better to make it more approximate the tangent? Can I make this a better approximation?
Alright, so to make it better, could he move the point down more? Like instead of having the point here, maybe move it to like here or something? I have no idea actually. This is where is he going with this?
How could I do it? Let's assume for a second that P is fixed, but Q is movable.
No shot, dude. Did I get this right?
You can move the point Q. I can't move P, but I can move the point Q. Can you move Q to make this secant line a better approximation to our tangent line?
Yeah, got it right.
Where would you move Q? Would you move it up? Would
Down.
you move it down? Let's look what happens. Okay, this is going to be interesting. So we're going to find out what happens as we move Q down this line. So if I move Q here, is that better or worse?
Better.
Better, because I'm going to have, let's use different colors here. That. This would be like Q sub 1, maybe a different point for Q. If I move it closer, is it going to get better or worse? Better. Okay. If I move it closer, it's going to get even better. If I move it closer, it's going to get even better. If I move it closer, it's going to get even better. When do you stop?
I don't know.
Can you move it really, really close?
Wait, do you stop at the point? Oh, wait, what the heck? Okay, that's trippy.
Can you move it so Q and P are the same point? Why not? Because then you only have 1 point. How many points do you need for line? We need 2. So can we move it close? The answer is sure.
So like all the way is wait, oh no, that's the infinity problem, isn't it? You can keep getting closer and closer, but it never actually stops.
We're doing it right now. Can you move it close? Yes. Can you move it so close that there's no difference between them? Yeah. Can you make it the same point? No. That would fail because we need 2 points. I don't care how close they are, but you need 2 different points, right? If you have 2 different points, you can make the equation of a line. That's great. That'd be fantastic. That's our idea, actually. So we're going to try to move the point Q really, 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 really close to the point P. If we can move it really, 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 really close, that's math speak, by the way. Really, 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 really means very, 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 very. If we can move it really, really, really close, then our secant line is going to be really, 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 really close to a tangent line. Do you agree with the idea? So you take this point, you go, let's move it really close. Not really far away, that's a sucky approximation. But if we move it really close, move that secant really close, that point really close, that secant is so close to a tangent line that it's not going to make a difference. That's the idea. So let me write some of the stuff out for you. So what we're doing right here, we need 2 points for a line, sure. We understand that. Awesome. So we have the points P and Q. Well, the question we're asking is, what happens as Q gets closer to P? And the answer is, as Q gets closer to P, we just talked about this, we just said this, this is nothing new. As Q gets closer to P, the secant line more closely approximates the tangent line. Now, have you understood that at the first? Okay. So as Q approaches, I'm going to use that word, we're going to use that word limits as well. Approaches, that means gets closer to. As Q approaches P, we get closer to a tangent, or in other words, the secant more closely approximates the tangent. Okay, well that's great. That's great. Oh, one more little note. Why was it that we can't just let Q equal P? What was the
Because you have to have 2 points for a line.
reason? Why
You already wrote that.
that we can't just let Q equal P? What was the reason? Why can't we just say, oh, let's move to P?
Because there wouldn't be a difference.
Okay, there wouldn't be 2 actual points, it'd be the same point twice, and that's a problem. You couldn't make an equation of a line with that. So one little note, we can't just let Q equal P because we need 2 points to make a line.
Oh, there we go.
You need 2 points. That would be a problem.
Can't let Q equal P.
Here's the idea of a limit, all right? This is a big, big idea. Here's the big, big idea for limits, okay? The idea is, how close can you get one point to another without them being the same point? So let's say I have 2 points like this. Can you find some space between it? Let's say I move it over to the midpoint. Can you find some space between it? Say move it over to the midpoint. Can you find some space between it? Can you keep doing that for eternity? Between any 2 points, there's a gap. In that gap, you can fill it in with another point. Because points have no breadth. That means that even though we draw them on the board like this, they really don't have any distance between them. So 2 points can get, would you agree, infinitesimally close to each other? That means so close that you can't put anything between them, but there's still some little distance, and then you can get even closer to that, and closer to that, and closer to that. Would you agree to that? So here's the idea behind calculus. It says we can get Q so close to P that there's literally no difference between the secant and the tangent.
That's crazy.
We can get it so close. We can't let it equal, but we can get it so close that the secant line is the same as the tangent line. That's the idea of a limit. Isn't that kind of an interesting idea? Yes, they're different points, but they're so close, it doesn't matter. That's the whole idea. So the big picture for our limits is, if we let Q get really, really, really close to P, the secant will be identical to a tangent. That's the idea. Or approximate it so closely that it doesn't matter. Really, really, really. If we let Q get really, really, really close to P, I'll use a better word, I'll use a more mathy word for that in just a minute. Really, really close to P, the secant will be identical to the tangent.
Secant line will be identical to tangent line.
Here's the idea, right? Here's the idea. Now I'm going to replace this really, really, really with a key phrase for you. The idea of really, 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 the idea of moving P or Q really, really, really close to P is called a limit. Moving something really, really close without actually getting there. That's the idea of a limit. You kind of understand the idea of a limit? We would say that Q would be in a limiting position. That means we've got it all the way really as close as we can to P, but it never touches P. That's the idea of a limit. It gets really, really close. So the idea of really, really close is a limit. In the most simple terms. This is it. Would you like to see an example of how to actually do this? Would that be interesting to you? How to find the slope of a curve at a point? You want to see that? It's kind of fun. Okay, we're going to work through this. I'm simply doing this to give you an understanding of how limits work and the jump that you can make, okay? We're not going to be doing a whole lot of math like this. I'm just giving you an introduction right now so that you see it's possible with some real math stuff that you've had before without actually teaching you limits in calculus. I'm going to make one limit jump in this problem. I'll show you when it is. But this is stuff that you could actually do. We're just going to use calculus to do it better. You ready for it? Do it more mathematically.
Alright, that's where we're going to end for now. So I'll come back probably tomorrow and finish this video up.